Okay, this is a problem that we did about a block on a ramp. And this time the ramp is on a table. All surfaces are frictionless, so the ramp can move on the table and the block can move on the ramp. And the question said, find a horizontal force F such that the block does not slide. It doesn't slide up or down. So we're going to move this thing with just the right force and get it to move such that the block does not slide up the ramp, too much force, or down the ramp, not enough force. And the problem sounds hard, but we're just going to apply the method that we have for these kinds of problems, and we're going to apply it methodically. So we'll start with object 1, which is the ramp, and object 2, which is the block. Object 1 has the force, gravity on 1 is m1g, gravity on 2 is m2g, and then there is the pushing force. So the pushing force on the ramp it pushes it left, and there's a contact force from the table. So the contact force from the table, so here's the pushing force, which is just called F in the picture, and the contact force from the table, so the force from the table is perpendicular to the table. Now, what makes this complicated, or at least trickier than other things we've done, is that there's also a force between M1 and M2, and it's perpendicular to the surface that they share. So the force of 1 on 2 goes away from that surface, and the force of 2 on 1 goes away from that surface. And this contact force, we can just call it 1-2, F1-2, is equal and opposite. These are Newton's third law pairs. So these two are Newton's third law. But once we have that, we can just turn the crank and apply our method. So the next step is to choose axes, which we're going to do. So we'll have x and y, which means that the vectors that have components in x and y will need to be separated into their x and y parts. This angle here is theta, and this angle here is theta. So we can do it pretty systematically here. The sum of the forces in x, the sum of the forces in y, sum of the forces in x, and the sum of the forces in y for object 1 and object 2. Okay, so here we go. For the wedge in the x direction, we have the pushing force in the positive direction and F1-2, but only cosine, not cosine, sine, opposite, 1-2 sine theta. And in the y direction, we have the upward force from the table. We have the downward force of gravity. And we have the downward force of the block on the ramp. So F1-2 cosine theta. For the block, in the x direction, we have only F1-2 in the x direction, so sine theta in the positive. For the y direction, we have a positive 1-2 cosine theta in the positive direction and a minus m2g in the negative direction. So the next thing we do is we're going to set all of these equal to the mass times the acceleration in that direction. Both of the y equations, there is no acceleration in the y direction. We were told in the problem that the thing only moves along the table. So acceleration is in the x direction, and because m2 does not move with respect to m1, they both have the same acceleration. So we get m1 times a and m2 times a. Okay. So this is the physics. This is really the physics right here. This is the setup, and on a midterm, this is most of the points. But what happens next is math, so we'll finish that up. And we were asked for, in this particular problem, what the force is. So, okay, I'll take this first equation since it's the only place the applied force shows up. And the applied force is F equals F1-2 sine theta plus M1 times A. So I realized that I can actually find what F12 is from this fourth equation here. Check it out. This means that if I solve for F12, 1-2, that must be equal to M2G all over cosine theta. So I'm going to plug that in now. So in place of F12, I'm going to write M2G all over cosine theta. And then I'm just going to keep writing sine theta plus M1 times A. Uh-oh, I don't know what A is either. Oh, well that's okay. I don't know what A is, but I can use this third equation and I can find that A is equal to F1-2 sine theta divided by M2. Oh, and I just found in the previous line what F12 is. So F12 is M2G all over cosine theta times sine theta divided by M2. So the M2's cancel, and I find that the acceleration is just equal to G tangent theta. So I'll substitute that back in. I'm going to rewrite this once again, and I get that this is M2G sine theta divided by cosine theta plus M1, and now A is just G tangent theta because sine over cosine is tangent. But now I have another sine over cosine, so I'll simplify this, and this is M2G tan theta plus, oh wait a minute, M1G tan theta. That means that the force is equal to M1 plus M2 G tangent theta. And that is the answer. Cool problem.